There you go. Cool, cool. Awesome. All right, probably once. All right, so we're going to get started with a FreeRTOS lecture. And quick question, actually. You guys are either doing or already done with the motor control PID lab, correct? Cool, great. I made that assumption, and I don't think I got it clarified beforehand. OK, so it's good. So first I'm going to go over is kind of a high-level overview. So nothing really going into the code, but kind of giving you what it is an RTOS is, what an operating system is, as well as the type of features that you can get from an RTOS. And we'll dig into what it is that an RTOS is and how to use it and how to create tasks like that coming up. So the first question is, what is an operating system? I'm asking this to you guys in here. I assume all of you guys have used the computer at this point. Can you guys tell me what an operating system is? Yes?
It controls processes, make sure they get the runtime they deserve, and then takes it away when they shouldn't have it.
Fantastic. So process management. All right. Anything else? Okay.
Maybe the link between hardware and software?
Yes, fantastic. So I/O, I think you see a hand there? Same thing? OK, cool, cool. Yes?
User interfaces?
User interfaces, GUI, desktop, what you see. Very good, very good. So actually, there's a few more items in there. For the most part, that's kind of what an operating system is. It kind of handles a lot of those things for you. There's a bit of a quote from Wikipedia. An operating system is a system software that manages computer hardware and software resources and provides a common resource for computer programs. So how does this fit in with Linux and Windows? With those operating systems, you get at least a file system, a user interface, a resource allocation, kind of going with what you were talking about when it came to the processes. Usually they'll handle some type of security, networking, hardware, I/O, multitasking, processes, and then also error detection, the blue screen of death, or a kernel panic that you might have experienced if you ever used Linux before. These are the kind of faculties and facilities or services that your operating system will give you on a system like Windows or Linux. But when you're in the embedded world, it's a little different. You usually don't need all these things. What's the difference between an operating system and a real-time operating system, an RTOS? An RTOS is an operating system that is meant for real-time applications. Now, the keyword here is real-time. It usually means that when you specify that you want a particular set of code to execute at a particular time, it will execute at that time. There's some other rules to it, and we'll get into that in a bit. But for the most part, that is usually what it means when you're talking about a real-time operating system or a real-time application. They usually have fewer services than a typical operating system. For example, they usually only have these three. A way to multitask, so that's some sort of scheduling. They have some means of allowing what we call tasks to communicate amongst each other. So you can think of that as processes, being able to communicate between one process that may be gathering information and then serve it over to another task that can then process that information. And then also a method for task synchronization. So if you need to make sure that certain tasks execute certain bits of code at the right time, they usually have some facility, some service that allow you to do this. That's kind of the difference between an operating system and an RTOS. And for the most part, beyond this point, we'll be talking mostly about RTOSs. And you can think of a task kind of like a simple function. Actually, they literally are, in this particular case, functions. And you can add them as a particular task. You have them run in parallel. I put air quotes because it's not actually going to happen in parallel. At the end, we'll kind of go into what it actually looks like for your system. So a bit of a diagram showing that you could have one task talking to another task, that task talking back, as well as one task sending synchronization information to another task. Okay. So some of the high-level benefits of using an RTOS. First one's going to be readability. Now, I know you guys are a group of electrical engineers, so I know you guys don't have as much programming experience as a lot of companies. We spend our entire college career doing a lot of programming. And one of the things that we kind of push a lot is for readability, and how readable and easy it is to understand someone else's code. Especially at Google, the only way for my code to actually be pushed into production is as someone who actually has readability, it's kind of like a certificate, who goes over my code and says, yeah, no, this is readable within our standards. So when you guys were doing your assignments, you were using timer interrupts to kind of do your timing for you, correct? So RTOS can kind of abstract a lot of that timing requirements out of the way for you. If you have a system that already has RTOS embedded in it, it's really easy to say, I want this particular function to run every millisecond versus having to set up your clock divider and then set up your interrupt service routine, and set up the nested interrupt vector, enable, stuff like that. You can remit all of that stuff that's already kind of embedded there. So it does a really good job of abstracting out that kind of tiny information for you. In generally, with an RTOS, just the process of using an RTOS can actually clean up your design. It forces you to have to think about your project as a whole bunch of different separate set of tasks. And we're going to have an example right after this particular slide in a particular scenario where we have to do that. It also helps out with modularity. And the definition of modularity when it comes to computer science or in programming is the ability to be able to mix and match and take away modules and add modules on the fly. If your system breaks when you try to add more features, it's not very modular. If your system breaks when you remove some features, it's also not very modular. Taking in and taking away features of your project should be pretty easy. So kind of a subset in modularity is code reuse. So if you have a particular function that says does a operation for you, let's say it does double calculation for you, and you know that you're using this particular equation all the time, the obvious thing for you to do is put it inside a function so you can just keep calling that function versus rewriting it over and over again, which has a couple of things that's useful about it. One, it means that there's no chance of you, as long as you had it work or you had it written out properly the first time, every other call won't have any issues with it. But also the benefit of actually making your code a little more optimal. If you have one function call in one area where the code's written to versus having multiple iterations of it, because it adds more instructions to your binary size. Maintainability. So going back to what I was kind of saying before, which was if you wanted to extend it or be able to maintain it, having it be modular actually helps out quite a bit. When your system's not so tightly coupled with each other, being able to changing small things here and there to keep it up and running as time goes on shouldn't be so much involved. And FreeRTOS can actually help out that quite a bit. These are, like I said, these are kind of high level, and it kind of takes some time with using FreeRTOS to kind of feel these benefits. But that's another little key thing about it, is it usually makes your code a lot more maintainable. Extendable goes back to what I was saying about being able to add more features, so you can extend it beyond a certain point. And one of my favorites is the fact that it's really good at being able to handle mixed processing requirements. How many timer interrupts do you guys have access to for your previous lab? 2? I heard 3. So 2, 3, a couple of those. FreeRTOS usually doesn't have really a limit to the, well, sometimes they have a limit to the amount of tasks you can have, but usually it's around 256. And there are ways you can bump that up to any arbitrary amount for the most part, as long as you have the resources to handle all those tasks. And you are ready and willing to take the brunt of the inefficiency of having so many different tasks. But you're not limited to just a few of these timer interrupts and peripherals. Usually you can run all this on one system interrupt and do all the switching for you in that particular context. Oh, and sorry, to get more onto the point with the mixed processing requirements, the fact that you have a certain set of tasks that do one particular thing. Let's say it is controlling a motor of some sort. You have another set of tasks that's purely just meant for controlling the UI for whatever reason. You can pretty much build a robot with this if you wanted to, and have you can separate all the different modules away from each other and be able to hit different requirements with FreeRTOS. Not saying you couldn't do that with normal software, but it took a lot more work on your part to be able to do that. And then functionality. It allows you to make your interrupt handling a lot more flexible, and I think Colin had taken your class. He told me one thing about in your class is like make sure your interrupts are as short as possible, which makes sense. We did that in our copy class as well. With FreeRTOS, typically your interrupts actually wouldn't do any actual work. They would make a call to the operating system saying, "Hey, I have this signal. I'm going to give you some information. You run the task that is sleeping currently. Wake it up and tell it to run my interrupt for you." So then it will occur. You have like a kind of like a one-liner that will then issue the command to the scheduler. Scheduler will then, when it wakes back up, turn on that particular task and let it fulfill your timer, your interrupt handling. This one's also pretty useful, which is the fact that you can also get your system utilization, so you can see how much percentage of your CPU that you're using by using FreeRTOS. Basically, with every scheduler, there'll be a particular task called the idle task, which is basically the task that runs when no other tasks are currently running. And by looking at how much time is spent running that task, you can figure out how much of your CPU you're utilizing for the most part. And then lastly, improve efficiency, ? Mostly because of the fact that improving efficiency doesn't always mean, using FreeRTOS doesn't always mean you're going to get better efficiency. Actually, a lot of times you can actually really, if you don't use it properly, you can actually get way worse performance if you use FreeRTOS. But if you use it right, you can actually end up benefiting the way that your code is written, and your efficiency either space-wise or time-wise. Okay. So now we're getting something that's a little more real, kind of out of the clouds. We'll go into a design scenario. In this case, the one I like to talk about is like a controllable assembly conveyor belt. So the idea here is that we have a microcontroller, and with this microcontroller, we are controlling some motor that controls basically a conveyor belt, and make sure that the conveyor belt runs at a particular velocity, not too fast, not too slow. It shouldn't slow down if you put an object on there and start to load it down. So we have several feedback mechanisms in the motor. It could be an encoder, it could be whatever for the most part. We have some network device that allows us to be able to chime in on that particular controller and be able to tell it, hey, I want you to run at this speed now. Or I want you to stop when, I don't know, when the time hits a certain time of the day. We have a keypad, some sort of display, as well as an emergency button. So if anyone ever jams their finger into the conveyor belt, someone can go over, hit the button, and stop the conveyor belt from running any further. With this, we're going to kind of go over into the situation. We're going to look at the situation in the case of without a scheduler, as well with a scheduler. And if anyone feels like I'm going a little too fast, or that you feel a little bit lost, just raise your hand and I can roll back if you need to. Okay. So without a scheduler, in this particular case, if you don't use a scheduler, you wind up reducing your executable size, which I'm pretty sure a lot of times for my classes and other classes, a lot of people don't really get anywhere close to the maximum size of their flash for the device. Usually they're pretty far away from it. But as you start to add more and more features and you add more stuff to your robot or more stuff to your Hyperloop system or to basically anything else, eventually start to gain more and more size and you might hit the limit. Once you hit that point, you can no longer add any more code for the most part. Having a scheduler will add more code to your executable, therefore it will get larger. So without it, you would have a smaller code size. Another interesting thing is that you have no reliance on third-party software. So let's say there is a bug, and the bug is actually in the RTOS that you're using versus your own software. You could go in there and try to debug it. If it's closed source for whatever reason, then it's kind of just like that. You can't really do anything about it. You have the executables. You have the linking. You're able to link it in, but you can't actually change it. And at that point, you're kind of at a loss, and you're kind of just at the whim of the company when they will fix up their particular problem. So that's one issue. Without an RTOS, you will typically save a lot more RAM and a lot more ROM. The ROM kind of goes back up to the code size. With the RAM, there's some utilized amount of RAM that the scheduler needs to use in order for it to function. So you wind up using up more RAM in this particular case. So these are all benefits, but to the negative sides, and maybe you guys have gotten into this or started feeling this when you're trying to develop your project, but it might be a bit difficult to cater to complex timing requirements. As your time requirements become greater and greater, like you're no longer controlling, let's say, one motor, but let's say a whole assortment of motors, or a lot of different things that are not exactly completely correlated with each other, like different systems throughout whatever system you're building. If they all have their own timing requirements, it could be kind of difficult to figure out how you time out your timer, and how you do your decision tree beyond that to make sure each thing gets chosen at one point. Whereas it kind of becomes trivial with FreeRTOS, or ARTOS for the most part. It also doesn't scale well when your complexity gets larger and larger and larger. During the development of a motor controller for like a rover for the robotics team way back when, we were trying to add more and more features to the system. But as we kept doing that, our timing requirements our timing started to get more skewed, and we're trying to fall kind of back. And it wasn't the worst thing because we kind of stopped. We didn't need to go any further. But if we kept trying to add more and more complexity, it was a lot more difficult to keep our time requirements down, as well as be able to keep the code maintainable for the most part. I believe this is the last one, which is kind of what I said before, which is the timing. Timing is hard to evaluate when you try to maintain the interdependencies between different functions for the most part. And that just basically means when you have no longer the requirement of just one device or one motor or one system to control, and you have a plethora of systems you have to control, being able to handle that all in your own code is basically building a scheduler, which is not a trivial thing for the most part. There are still people adding and improving schedulers every day. So that's pretty much the game plan without scheduling. To kind of give you guys some perspective, kind of imagine if you guys didn't have access to a timer interrupt, do you have a way to kind of tell how long time has elapsed? We didn't have a timer interrupt for your last lab. And in that last lab, all you could really do is do like a delay. And you had to ensure that you always ran your code at 1 millisecond or 10 milliseconds duration, or 10 milliseconds between each time you sample and then read and then try to change the PWM or the power output to a motor. You kind of think that as you add more and more functions into that list and you try to do delays in between them, it gets a lot harder to make sure they're all right at the point where they're supposed to run. It might get skewed over. Let's say one function has a couple branches that makes it take a little longer. All these things can cause a lot of issues, and those are the kind of things you have to worry about when you're writing without scheduling. Now, when you are using a scheduler, it's usually pretty simple, segmented, flexible, and maintainable. So you can kind of separate everything, all the different components of the system into tasks. If you kind of go back a little bit here, each one of these items here can be its own separate task. There would be one just for controlling the motor controller, possibly also handling the feedback loop as well. That could also be its own task as well. You have one for talking with the network device, another one for communicating with the keypad, another one for working with the display or controlling it. Another one just for, a section should be on interrupt, and then once it fires, have another task that's basically sleeping or waiting to be issued or commanded to do something, and it'll do its work. So each one of these can be turned into their own task, versus trying to use two timers and trying to push these three into one timer function and trying to push these guys into one other timer interrupt handler. Another thing here, another plus is the fact that the processor utilization is automatically switched from task to task on the most urgent basis. No explicit requirement, with no explicit work on your side. So when we kind of get into how we format the task, we'll go into how you can give different priorities for tasks. So if you have a higher priority task that needs to run right now, you can have that task run over your lower priority task, like let's say sending some telemetry feedback to your home base. The event-driven structure of an RTOS can allow you to ensure that no CPU time is wasted when you're polling for events. I'm pretty sure quite a few of you guys probably had to poll on your ADC, so just do a little tight while loop until the thing is finished. I'm trying to think of another case where you guys had to possibly poll that particular assignment. Can't remember off the top of my head, honestly. Actually, no, I think the keypad. One thing that you could do here is you set that up for an interrupt, and then when the interrupt fires, you can have a task run from that. And you might have actually had that set up for this previous lab, but it gets a little easier with FreeRTOS. And then processing only happens whenever there's work that needs to be done. So that's another part of this, is the fact that since it's event-driven, you can basically say, on interrupt, send an event to the schedule, and the schedule only does work when an event occurs. So that's really useful as well. Potentially, power consumption can be reduced if you use the idle task to put your device to sleep. You don't need to be constantly waking up and doing stuff. You could just, let's say you're only going to work every hour or every couple minutes. You could use the idle time to go to sleep, go into low power mode, wait a little bit, and then come back out of sleep whenever you wake up again. Core functionality will be, so this area here is more of like a, could be better, could be a little worse. There's some considerations you got to take into this. To end up using the scheduler, there will be some resources that need to be used by the kernel in order for it to particularly work. And the amount of efficiency of every call to your function kind of depends on your kernel tick, which I think we'll go into in a sec. One other thing about this is that this solution requires a lot of tasks, which require their own memory, their own allocated memory to kind of work properly. And for or foremost, it'll end up requiring a lot more RAM in order to run properly. So the big negative part here is the fact that you end up losing out on a lot more RAM because you usually have to make a bigger allotment of space for each one of the tasks that are running. Oh, actually one more. Oh, and this is one that I'll go into later on, which is the fact that frequent context switch change between tasks of the same priority can waste processor cycles. So far, even though I've been using the word I kind of between FreeRTOS and RTOS, I've been really talking about RTOSs in the high level, just any type of RTOS. And there are a lot of available RTOSs out there. One of them, the one we're going to go over today, is FreeRTOS. is free. It is open source. You can contribute to it if you like. It is pretty much available to anyone. And honestly, most, even big companies like Google, we just use FreeRTOS. There's no reason for us to try to reinvent the wheel. There's no reason for us to pay millions of dollars to get a particular type of RTOS that's really not necessarily what we're doing. And honestly, more and more people around are just using FreeRTOS for everything, so it's not a big deal. But if safety was a concern for you, there's a thing called Safe RTOS. So let's say you're deciding that, oh, I want to be an electrical engineer for biomedical, and you're trying to figure out what type of software stack or firmware stack you're trying to use. And you're like, oh, I know, I'm under my 138 class. You heard about FreeRTOS, but also heard about Safe RTOS. Safe RTOS is a safety critical operating system. It is meant to be highly redundant in a lot of different ways, to the point where I actually don't know too much about what makes it very different from FreeRTOS for the most part, because I haven't really had any particular use or need for it. I've got friends who end up having to use Safe RTOS because when they're writing stuff for writing code for biomedical devices, there's a certain standard you have to follow for everything. And then lastly on the FreeRTOS stack, which is Amazon FreeRTOS, which is very new. I think it only kind of became a thing a year or two ago. I think it's only been a year. Amazon just recently acquired a company that built FreeRTOS. They made their own RTOS, and it's basically meant for the Internet of Things for the most part. It is also free. It's also open source, so you can contribute to that as well. So if you think IoT is interesting, that might be an interesting thing to look into. Oh, last thing. If you know FreeRTOS, you pretty much know Amazon FreeRTOS. They're just adding more stuff to it for the most part. Now, here's another one that's very common. This system is actually used for, I'm trying to remember which rover on Mars right now. I think it was Discovery. But NASA used VxWorks for NASA. The only thing is, I think Lam Research also uses VxWorks. Only thing about that is when I had my interview with them, they asked me a couple questions that were actually very specific to VxWorks, and I was like, there's no way I would ever know anything about VxWorks. It's not free, it's not available, it's expensive, I have to pay, like, and I'm trying to find like a single license, I can only get down to this amount. So like, yeah, there's no reason for me as an individual to want to even learn VxWorks when I have other solutions like these up here. The next, I didn't have the time to find the cost of the X, but it's also quite expensive. It's proprietary, so it's not open source, it's a little easier to get your hands on. And there's also TI RTOS, which is free and open source, well, Ash is open source. You can download the source, and that technically makes it open, but there's no community, it's not on GitHub, so you can't contribute to it, can't improve it. So if there's any issues with the system, even if you can improve it for yourself, but no one else gets to benefit from those improvements as well. So unless you send it back to them in a zip file, and they're like, oh, I guess it looks fine. So those are the different types of RTOSs that I kind of about. From what I've observed in all my previous jobs, the world mostly working with FreeRTOS. It is the #1 most popular real-time operating system out there at the moment, just used by everyone. Yeah, so. Oh, and they also have support for like a load of microcontrollers. So it's very easy to just port it over to your microcontroller. Not all microcontrollers, a lot, just a load of them, a load of microcontrollers. Like they have a good set of the Ant controllers, a whole bunch of like the ARM M-series microcontrollers, a good portion of the TI, Expressive, which is the people who made ESP32 with their extensive architecture. There's an RTOS for them. So there is an RTOS for most things. There's also FreeRTOS implementation for Linux as well.
So for these FreeRTOS, when they release it at the high-level language written in C, so you just compile for whatever machine you want to run now?
Correct. Yes. So there's a particular small file when you're trying to port it. For the most part, there's a base file that goes through all the implementation of everything else, like scheduling and doing the task communication. But there's a file called the port.c, and within that file would be everything that includes how to switch between tasks, how to set up a system timer to run the RTOS on, and pretty much the whole shebang that you'd ever need for getting the RTOS up and running. If there's a microcontroller if there is a microcontroller that's not supported for that particular for FreeRTOS, you have to build the port.c file yourself, and it's actually non-trivial. It's actually quite a bit of work to do. But if there's like, ARM Cortex M4, if you have an M4 system like an ST32 or what's the Atmel SAMD21? Do you guys know what that is? Anyone? What is it? M0. Okay, so M0. That's also supported as well. So if you need an M0, you just take that over. You do a little bit of tweaking here and there to make it work specifically for your use case, and then you're pretty much good to go. There's a couple of config operations, some macros you have to just change to 0 to 1, and you'll get your stuff up and running. I actually did that lately for one of the boards that I made for the copy department. So.
Good question. So the set RTOS, is it like in terms of time that you're going to execute a task guarantee, or why is it set?
Yeah, from what I remember when I was reading this up a while back, it has to do with certain guarantees about how the software is written. So there's an ISO standard for when you write software for medical devices or for like things in the military or things for like aeronautics like that. So it's kind of like thinking about designing a circuit for that's flight ready versus just a circuit that's for prototyping. That would be the difference between the two. So there's more care taken into making sure that it's very unlikely that you get into a deadlock or into an unsafe mode when you're running with, say, FreeRTOS. Whereas FreeRTOS, if you use it long enough and you don't get enough stack or do a couple things here and there, you'll get a lot of issues here and there. I think they also give a lot of support so that there's anything that does pop up, they can kind of help you out directly for that one. Whereas FreeRTOS, they have some forums, and you can ask them questions there. They're actually pretty good at answering back, but there's some weird quick kink in there. It's not the biggest. They don't feel like that's the biggest deal. The normal FreeRTOS. Any other questions? If you guys are like confused on anything, should we go in and I can go over something before we go into the implementation? So how do you implement tasks and stuff like that? Cool. Okay. So what is a FreeRTOS task? FreeRTOS task is literally a function that is added to the FreeRTOS scheduler using a function or API called xCreateTask. A task can have the following things. It can have a priority level. It can have an attribute of having an allocated amount of stack or allocated amount of memory to run whatever preliminary task for the most part. It takes a single input parameter, so you can pass in information to the task on its creation. It has a name, so you can, if you did a dump of all the different tasks that are currently running, you'll be able to see its name to kind of be able to identify it. And optional is a handler. This is basically a data structure that you can use in order to replicate that task again. So if you wanted to kill the task using xDelete task, or xTask delete, or using xTask suspend to suspend that particular task, say go to sleep for now and just don't worry about anything at this point, you can use this handler to figure that out. So those are the 5 things that you need to keep in mind whenever you are creating a task, is those 5 things. This kind of gives you an idea of how you go about creating a task. There are some C++ 11 things here. If you don't know them, I'll just say them really quickly. For the most part, you'll define your FreeRTOS task. The return type void is returning anything for the most part. And it will take a void pointer as input. Even if you don't plan on passing anything, it must hit this function signature in order for you to be able to pass a task into FreeRTOS. And this is kind of a very general, on the website they'll actually show you something that's just like this for the most part, but it doesn't have to be this way. So you can make your task however you pretty much like. But for the most part, you start off with guiding your parameters, or parameter. In this case, I took a void pointer passing into UMW2 that's a passive number to this task, and it's just a parameter. It can be anything. But at this point, I want to grab my parameters and do whatever I need in the first stage. The next thing would be to define any constants that you're working with. In this case, let's say I have an increment count of 20. You can put that here, and yeah. After that, define your local variables. After that, you want to do your initialization step. Whatever you need to do, maybe set up some variables or possibly set up some hardware, turn on some LEDs, set some GPS as outputs or inputs, so on and so forth. Then finally, you have your loop code. So we'll be looping over. If you guys have ever worked with an Arduino, you can think of this section here as being the setup, and this section here as being the loop. And this little area right here is only necessary if you plan on allowing this particular task to die. If you have a while loop here, and let's say you have a break statement in here to say like, okay, we're done with this while loop, we're going to jump out of it. If you don't leave X task delete at the end of this, it will result in system crashing. Really, because the system will continue to run through instructions until it finds some invalid instructions, and then your system will hit a hard fault for the most part. One little key thing about the API is that if you put null here, it will delete your own task. If you put a handler here, it will delete the task that you put the handler for. And like I said, it's just another variable that you can assign that you can use as a way to reference your other tasks. That's pretty much the RTOS task declaration. Super simple enough for the most part.
That's a good example of the times where you set it up for this task.
Nice. That's a good question. So typically for your architecture size, a void pointer will be the size of 32 bits. For ARM cortexes, they're all 32 bits for the most part. Build in that kind of system. If you can just fit whatever number you like into the parameters, into the void pointer, you just throw whatever number you like in there. Or let's say up to 4 bytes, like letters or charts, something like that. But a lot of the times, typically you wouldn't really do that. A lot of times you'd actually pass in an address to some other larger object. Let's say you have some structure. So let's say we have some struct, and I'll call it order data. And here we have a unit 32, 30, tick count. And this is very unnecessary. Why we want to keep like the A and B ticks for encoded, but I'm just putting in some values here. B ticks, maybe like a double for speed or what have you. Just a whole bunch of information that you want to kind of pack in here. And if you wanted to pass this into an a crate for this, you basically take, actually I'll kind of show you in the next slide, but you would take the structure, you initialize it, you create the structure, you initialize each one of the variables here, however you like, you could pass the entire structure into the task, and then it would then use that address to grab information from it. So a lot of times you just pass certain larger objects into your pointer and allow it to do its setup. Oh, and the important thing would be that, actually I'm not going to say. You will most likely steal the data. So go to MD here. I will pass in the address of MD. So now I have it here. Don't do my task. I have to cast it into it will come in as a void pointer, which is pretty much a pointer to anything for the most part. So I need to cast it into the object that I know that is being done. I know we passed it. So so much of the code I would have a the C way. Mode data asterisks, parentheses, P, V, colon. And that would be and you use triangle, arrow, and then get all the different elements flowing back to the structure from there.
You don't have to hard code all this information in the itself.
You don't do that too.
Then I don't need to do any of this. Like you can jump right into this one.
No, absolutely, yes. So if you don't need it and stuff, you don't have to. I'm saying like if you're going to organize it, you would organize it in this fashion. So you would just be, if you didn't need to require any parameter, don't add any parameter. If you don't need to define any constants, then define any constants. Any local variables, if you don't need it, don't find any local variables. If you don't need to initialize any hardware, don't do that, just run your loop. Honestly, if you actually make a task that doesn't need a loop either, you just have it run through one shot and then delete itself. I've done that when I was writing some task handlers for web responses. So I get a message over from someone from the web to my device. My device would pick it up and say, okay, I'm going to hand off this information to this task. The task would then do a one-shot, go through, do all the work of serving up the HTML and stuff like that to the person who requested it, and then it would delete itself right after. This just allows that I can keep creating more and more tasks to handle more and more connections that are coming up. A lot of times you would pass in a parameter that would indicate or tell the system how to properly act. So a lot of times in my class I tell my students to define some parameter that allows a task that's mostly the same. It can do two things, but the two things that it's doing are mostly the same. Have it just change it based off a parameter you pass. So let's say you have like the parameter is going to be like check safety afterwards. This isn't some signal you have to check after you're done with this loop. If there are some cases where you don't want to check that safety, and other cases where you do want to check that safety, then you could pass in a parameter and either check it here. So the function is the same thing. So I have to rewrite the entire task again in order to do the separate actions. So that's what you can kind of do with the parameters passing. It's up to you and whatever you decide to do for yourself there. Oh, and another part of this was, that was actually the particular case where I wanted to pass a particular structure to two tasks, but I didn't make it global. And it's just a very common thing in computer science to try to keep your namespace, your global namespace, as clean as possible. It's a thing as you get deeper and more advanced inside of code where when you build larger and larger systems, having all your variable names in the global space becomes an actual issue. But for the most part, it's not that big a deal. So, any other questions on this one?
For the test, would that mean to be executed at a certain frequency?
Yes.
Not well one.
Yes, this is.
But it's just like a one-shot deal, then you don't need that one.
Correct.
If it's a while, then the schedule will chop it, right?
Correct. And I'm going to go into that a little bit, like, near the end of this, but yeah, I'll be going into that very soon. Alright. The rules for FreeRTOS. If there's anything you leave here with, I tell my students all the time, just remember these rules and you'll be pretty set. Okay, you weird things with FreeRTOS, just keep remembering these rules. Rule number one, the highest priority ready task runs first. What was the first? Oh, okay. This is the one, I'm sorry, that one's first, that runs. If you have two tasks of equal priority, they'll be time sliced. I'm going to show you a little bit of a graphic that will show you what it means to time slice through. So for the most part, the highest priority task always runs. So if you have two tasks that you created, and one of them has priority 1 and one has priority 0, the one with priority 1 will be running on the CPU, whilst the one at priority 0 will be kept away from running. And I'll go into more details about like what you want 0 to run at some point. I'll go into that in a bit. But if they're equal, it'll be time sliced, and I have a graphic for that. Should put on this page. Lower priority tasks only get CPU allocation when a higher priority task is sleeping, blocked, or suspended. And a task can sleep in various ways, and a few of them are this. Explicit sleep, in this case, let's say you want to run at a particular frequency, you could say vtask delay, and that delay would be 1 OS tick. And the OS tick is defined by, well, pretty much whatever you want to define it by in the beginning. Typically it's set to 1 millisecond to 10 milliseconds. And I don't think anyone around the industry ever changes those. It's usually 1 or 10, and on really rare cases would you make it any different. It can. I'll go into the reason why you may not want to do that. But typically, having like a frequency of about 1 kilohertz is very common. But you can always slice it in half and then have it run at 2 kilohertz or even 10 kilohertz. I've done it before, but you will see some issues there. Well, depends on how fast your CPU is up. Yeah. You can also do this by sleeping on a semaphore, which I'll go into on Thursday in more detail. It's basically a signal that tells you when to act for the most part. So you can either sleep and wait for that signal to come up. You can also sleep on in the event that a queue is empty. So if you're trying to pass information from one task to another task, you call those queues. And let's say you try to read from it and it's empty, you can sleep on that as well. You can also sleep on it if you're trying to pass information over to some other task. But you notice that that queue is full. You can't fit any more information in there. So you can just kind of like say, all right, I'll wake up when you're done finishing reading off all the stuff today. And kind of use a bit of a diagram here. When you first get a task, it'll start off as ready. From here, depending on the situation, it'll be most likely it'll be running. So let's say you do a sleep at some point. Let's say you want to have this thing run at a millisecond. You can do a sleep, which is going to move it into the blocked phase, just blocking on, just waiting for a second millisecond to go by. On the event that second, that millisecond has occurred and you've already waited that time, you can go back up to ready, and it's going to do things, hey, it's your time to run, we're going to put you back into running, and start running again. This is the most obvious cycle you'll probably be putting tasks into, either blocked or running or ready. But there's also something you can do, there's another thing you can do where you can just turn off the task and just not let it get any schedule time at all, or the CPU time at all. That would be to run the view task suspend, or view task suspend. Basically, that'll put the task in the suspended state, and if you ever run view task resume, you can bring it back. So you can say it's kind of a play and pause on that particular task. So a couple ways that you can, again, be able to allow a lower priority task to get CPU time is that, let's say the high priority task did ran its job, ran a couple instructions, and then it called the task delay, it was in sleep. Now the rule of the highest priority task, which in this case would be task 0, is now ready. So that's kind of the way that you can have different tasks to run at different points in time.
So do you suggest that the view task suspend and the view task resume will be in your concern, or that is something on the outcome already that you don't have to worry about? The user won't know where to insert it, right?
Actually, the application designer would be the one to kind of assert when they want to use it. The RTOS really just handles moving things in and out of these states. It doesn't do any of the work that was wrong. Really making the call to block, or the call to suspend, or the call to resume. The only real thing that in this diagram that it affects is when the blocking events gets unblocked. If something changes, they say, oh, this is no longer a situation, no longer supposed to be delayed. It would move it from the blocked to ready. So that's really the only thing that influences. Otherwise, you will do API calls to purposefully suspend a task, or purposefully resume a task, or purposefully delay yourself, or send information to one task, so on and so forth.
So back to your model example, right? And there's also a time you want the model to run.
Correct.
And you want the model to be system. So then you put something on it, it's still like in a static speed and everything. But sometimes you also want the task to go back to suspend or something so you can check the emergency button or something. Is that what you actually have it suspended?
The interesting thing on that one. So you probably have your emergency button on an interrupt, and when that interrupt fires, you then run the highest priority task. Correct. So the drive task would be interrupted, and then that higher priority task, in my imagining, would be set PWM to 0, doing other safety checks to make sure everything's turned off. It could also potentially suspend the motor task, or it could just hold itself and not ever block. If it ever blocks, then it's always running. So those are the two options: either suspend the other task and kind of let the other tasks communicate to unsuspend the system, or potentially just hold the system down and wait for someone to unpush the button and allow the system to come back. So
What you said seems to imply that the supervisor test.
Oh, there's a scheduler. Yeah, the scheduler is the one that supervises the system, and every system tip or every timer tip, it will come back up. It will do the work of figuring out which tasks to run, and then it'll swap them out.
So on top of that, you mentioned that it's a standard task.
Yes.
So scheduler is kind of working in the background. So I want to write a code to suspend this test.
Yes.
At certain conditions, right?
Yes.
So this code itself is a test.
Yes.
So this test is different from the motor control test because this test seems to control which test will be activated, which one should be blocked, right?
Correct.
So is that always the case? You have a test that's defined as kind of a somewhat of a supervision kind of a deal.
So on that particular case, it's not in all applications where it's necessary, but that particular design pattern, the watchdog design pattern, and have you guys know over watchdog purples at all? Okay, not at all. It's very common for a lot of MCUs to have a watchdog timer. It actually waits for, you have one process that keeps waking up to basically feed the watchdog, And then if the watchdog does not get fed, it'll get angry, it will reset the system or run an interrupt or something else like that. But it's also very likely that a lot of people will implement a watchdog as another task, a supervisor task that basically watches the system to make sure that if any tasks are what we call starved, basically they're always blocked. They're always blocked because some higher priority task never allows them to run. It could then the supervisor say, hey, like, there's something wrong with the system, send an alert to the user or to whatever actually needs to be done when that happens. Yes, a watchdog design pattern is quite common and out there, but it's not always necessary.
So something like a defect sustain or a defect return. That function is called within a certain test.
Yes, correct.
So that test seems to have a higher authority than
Correct.
that little test.
Yes.
That
Although
based on specific maybe one single purpose, like multiple.
yes. And actually, one thing on that is that like any task has the option to use any one of these. So there's nothing in particular that you do differently in creating the tasks or declaring them. So it is in how you write the tasks themselves, for the most part, that makes them different from each other.
So how do you guarantee that after it's suspended, some other task is running, that you can resume yourself?
I'll get into that in a sec. Yeah, I'll get into that in a sec. I think the next one should have. So as we go over this, and then the next one should have kind of a little of a diagram I can go into that a little bit. So adding a task and starting the scheduling. So this is your main. You allocate a certain amount of step. This is not so right here. This step size is in words, not bytes. So whatever the register size is, that's the amount of that's the multiplier for this step. So in this case, you have 4 bytes for your register size. It's 4 times 128. You pass in the function, basically the function pointer. You pass in the function, you pass in the name, you pass in the amount of step you want to allocate. You pass in whatever value you want to send. In this case, I pass it as a void pointer, a 1 for the most part, in this case. This is a macro for the idle task. And then this is a handle, which I didn't actually define in here, but basically this would be the name that I can use to be able to suspend that particular task if I want to. So I do X task suspend, X handle. And this would be whatever name you like. And once you've added all your tasks, then you would do the task start scheduler, and the scheduler would start, and the highest priority task would run first, and then just keep going through until the system turns off, or whatever else happens to the system.
So this example, you don't say we want that.
Correct. That's useful, but this is kind of showing as an example. So you have tasks of the same priority. This is kind of, think of this kind of like a timeline. You should actually descend beyond this point, descend beyond that point. But if you have tasks of the same priority, they'll be time sliced. So the OS tick frequency is something that you define in FreeRTOS. It is a FreeRTOS config.header file, and then you can specify how long you want a OS tick to be. I believe it's in hertz, so you just put like a 1,000 for 1 millisecond for the most part. It's very simple. If you have 2 tasks of the same priority, for the most part, you can't guarantee that one or the other will be ran first. Typically, the first one that you add will be the one that runs first, but that is it's supposed to be undefined. So never guarantee or never assume that that's going to be the case. Otherwise, your system might not work properly. So in this case, let's say that task median 1 will run first. It will run for its OS tick amount of time. Then the scheduler will come up. So the duration time will be the scheduler coming in. Taking the task that's currently run, I won't go into more detail about this on Thursday, takes a task from the system, takes a copy of the CPU, puts it into RAM, puts the copy of the other task into the CPU, so basically rewrites all the registers to what the state was prior to run, and the state didn't have RAM, so it's pretty much put it. And this time here, the M2 will be controlling. There's one for its OS tick time, and then the next one will run. So it's time to use up, so it runs, so it's kind of flip-flop in each other. This is called round robin. And for the most part, it will cycle through, let's say you have 15, and you cycle through each one of these, and you go all the way to the front and cycle back. This.
So the problem with that is one batch process starting them porting other short processes.
One of them, in the case of the same priority, it doesn't have it.
Same priority.
Oh no, it can't. This task can be interrupted for the time. So no matter what it's doing, It's only allowed to run for about a millisecond, and then the next task is allowed to run. So now it runs for 1 millisecond, then interrupt fires, the task is swapped out again, and this one can resume running. But even though it's a fat task, it doesn't really change the amount of time that gets to run. If the different priorities, though, it's a different story. And to the point that you brought up, and this graphic that I made is not the best. I should have really said that this section here, if I would kind of cut this here, I would consider this part to be the schedule time. So every tick, if you set amount of time that's required for the scheduler to figure out who's next task to run, it's a bit of a mathematical issue trying to figure out. And then once you figure out which task is next to run, then you need to set up the system to be ready for the other task to run. And then when you do the interrupt return, it'll actually return you back to whatever position of task 2 function that you left it. But as you begin to make the OS frequency smaller, this schedule time stays around about the same, as long as the frequency doesn't change. That schedule time is the same, but the amount of time your other task can run gets smaller. Then you hit the halfway point where now half the time is spent running the scheduler, and the other half's actually doing meaningful work. Now, this is not to scale, usually it's a lot smaller, but if you keep increasing the OS tick space, you end up using a lot of time and overhead switching out tasks versus actually doing meaningful work.
So if I set it to 1 millisecond, what is the overhead that time?
Depends.
Like 1%, 10% of the 1 millisecond?
I should actually do this demo, and I might give you the answer on the
cycle that you need to system pop, right?
Yes, precise. That's pretty much it. And I actually don't know off the top of my head right now. I think I had a friend who looked that up, told me a number, but I'm not going to just pull that out of my butt and say, oh, it's this. But I know it's supposed to be really small. Usually when you do the port.c file, you try to really take advantage of whatever instructions you have available to optimize the amount of time it takes to get those answers. So that's pretty much that. I will hopefully have an answer for you on Thursday. Yeah, once you have that answer, you can kind of figure out like what's your maximum or what space you feel comfortable with, if you want to increase the OS tick frequency. Now, to kind of go into the case of where you have a really fat program that's running or a really fat task that's running, if you have tasks with different priorities, this could happen. Where, let's say, task high priority, never sleeps, never blocks. I'll say, never sleeps, if it's blocked, if it's suspended, just keeps running. Then the entirety of its runtime must be over, and your task low will never get your time to run.
This is even true when EL is scheduled every so often. That's already expired.
Correct. So there are OS ticks that keep happening. The scheduler will end up coming in, intervening, saying, okay, who is now the highest priority ready task? This one was never blocked, so it's still ready for the most part. It was running, then it went to ready. This task is ready, because the assumption here is that this guy wasn't blocked, and he's configured and use it. But this one is the highest priority, therefore this one continues to run. So it just says, oh, next one to be scheduled is TH. TH just run in. Then another OS tick happens, okay, who's next? TH. Another one happens, who is next? TH. So it keeps doing that over and over again. So a little bit of wasted cycles in that recalculation each time. So that's where you kind of lose some efficiency depending on if you really design it really poorly. That's the overhead that you take in order to be able to design your code more functionally, where you can have separate tasks for each one of those different modules, as well as also being able to really easily pass information between them. And we're going to be on this, and that's for next week for the most part. Any questions? This is pretty much what I have for this week, and the next week I want to go into a little deeper into how the task swapping kind of works. Then I'll go into how you communicate between tasks.
Now, where do you find the priority? Right before the design?
Right here. So usually you put the number 0 here. I usually use task idle priority, and I do +1, +2, +3.
What priority is it?
This one is the idle priority. And honestly, I should probably change that. It should not be idle priority. It should be priority +1, when something is non-zero for the most part. Just because of the fact that the idle task is a bit of a it's a bit of a special task. That one's the only task that's actually special. And the Wi-Fi task isn't really special, but that task is special because there's a lot of statistics that kind of run in that case, and it's just usually some tight waiting for something to kind of happen. But you can put another task in the same priority, and then you can do whatever you like in that task. But If you put yourself at the idle priority, the scheduler will schedule you for running that time. But it's generally preferred that you only have one idle task, and you keep all the tasks outside of the idle priority number. This is how you define it. Just whichever task is the highest number, is the one that gets run first. Just a run at that next schedule.
When I run my code, I often put in my priority, the period, this is at the fifth time here, maybe not for all the period, and also the end time. I'm not sure how you have the end time to control it, because then I know how long it takes. So like, that much period. So then I guarantee that it would happen before let's say 30 milliseconds or something. Otherwise, the meaningful end time.
Actually, can you say it one more time, because I think I might have missed the beginning of the question.
So then typically when I roll my endpoint, it's passing the priority.
Yes.
So I know that my task has a priority. Yes. That I have a certain window that I allow other tasks to come in. That I assume now you have a peak time to pick up that, right? So then the scheduler will, suspend my own task at the certain task time, right?
Correct. So so for a small duration of time, the other task will stop its actual function,
Right.
and then you'll go in, the schedule will run to see who's the next one to run,
Right.
and then if it decides you're not the one to run and someone else, it will then move that one into the CPU context.
Right.
And in the case where things can kind of break down, where if you put all the tasks at high priority, all the tasks at medium priority, the RTOSness of this kind of goes a bit away. For example, you obviously want to make your loader task higher priority compared to the rest of the tasks. At that 1 millisecond or 5 milliseconds or whatever time you want that thing to loop on, that extra time that's left is what the other tasks are allowed to use. Also, you can download. But for the most part, you put that as you put that task highest priority, have it sleep, and during that sleeping time, all your tasks may do their work. And they'll be looped in as you set the priorities for them. So if you give all the other ones all medium or low or whatever priorities, they'll get the motor task, then the next one, then the motor task, then the next one after that, and it's going to loop through those for each step.
Right. So then my next question is that now I want TN1 to finish this at before 30 milliseconds. Because I know that TN1 is going to have to pass on the result to another task.
Okay.
So how do I guarantee that will happen?
So you want TM1 to do what exactly? You want it to finish?
By 30 milliseconds.
Finish by 30 milliseconds.
Right. Is there a guarantee that I can have that functionality and happen?
No. Unless you decide
We are integrating, right? So then I have the task that meet the result from the first task, so it can continue.
Oh, yes. So that would be going into what we would talk about next week, which would be on semaphores. Yeah. So the idea here would be that you can't really guarantee that your task would finish in 30 seconds or 30 milliseconds because that depends on how you load it. But if you have other tasks that, let's say they're waiting for some information and you need to have that process before they can do anything, you have a semaphore, you send that signal to the next task, and that would allow that task to continue running. Yeah, I got the information, I got a signal to say go, and then I'll go start running. And I can take whatever information you might have set for me somewhere else.
Basically sets it to ready.
Pretty much. That task in particular will be blocked. It would say, I'll block myself and I'll only unblock when I get the signal. And the other task could say, hey, I've got the data that you need, and set the signal for you.
So can we go back to the slide where you have the wireless?
Yes. Yep.
So can I assume that my resuspend and my resume will be somewhere in the wireless, or where is it going to be inserted?
Are you saying like this is like a mode task or something like that?
Wherever the task. I want to be a good citizen, right? I don't
Yeah.
want to hold on the world forever. I want to be able to set that somewhere, right?
Yes. I would actually say that so btask suspend and resume are a little rare to find. Typically you'll use things like btask delay or btask take semaphore.
Basically, you create some idle time spot for other people to come to.
Correct. So you have like this btask delay in here. So let's say they put like 1 for 1 OS tick or 10 for 10 OS ticks, something like that.
So is that a rule of thumb that, how many days you're going to put in there, or practice?
It is too application specific to say that, honestly.
I don't know.
Yeah, it's supposed to like I don't need this thing to go on. If I'm gonna toggle it LED, then you toggle it like 5 times a second, and that's kind of immediately obvious. Yeah, 250 or 200 milliseconds or 200 ticks. So it's one of those things where like it really depends on what you're doing and what you need, when you need to see the actual run. And if you needed it to run faster than 1 kilobit, then you can change the task frequency. That's like hand over here.
So there must be some indication along that your idle test never get to zero time for idle test. Some lower priority job never get run. Is it some indication like you're just asking the CPU to do some impossible thing? The CPU is too slow.
Absolutely. And one thing about the normal FreeRTOS is that like if that's happening, you'll just kind of notice that that section of code is never being executed. But there are methods that you can do in order to detect when those cases happen. For example, you could have your idle task, and it's a particular area called event groups. But to kind of simplify this, you would have a good portion of the tasks, let's say the tasks that you actually really care about, you'd have all of them send a certain signal to the watchdog task. The watchdog task, when it gets its time to run, let's say every 10 milliseconds, it'll rise up, say, okay, let me make sure that everyone sent me a signal, and if anyone's not sent me a signal, then I know that that someone's blocked, or that particular task is blocked. If I only really care about the idle, like I want to like if any tasks are blocked at all I need to do is have idle give me the signal. If idle gives me the signal, then I knew that at some point all tasks were kind of sleeping, and idle was run. If idle never gives me the signal, then I knew at least definitively that at least some tasks above it were blocked, and idle never was run, or maybe idle was never run. That's another type of design pattern where it's another thing. That's another extension of the watchdog where you would have different tasks basically indicate that they are still alive and they're working properly. And if they weren't, then you can make some action, do something to fix it, whatever that might be.
Is your compiler be smart enough to detect that part of your static problem before it happens?
No.
Because processor specific, right?
Yeah.
You have a time, the speed, and everything. But you're violating that, then the compiler will be able to detect that. I don't know.
that is a.
Yeah, but that's something that boils down to how much time you need to run, and then you have to be exceeding the limit of the CPU can execute and handle all that, right?
But the high priority task is externally triggered, and even the compilation time, you don't know how often the external signal trigger that.
So I'd say on the fact that in order to actually because I'd say that some part of my work was doing a lot of like metaprogramming, basically like doing a lot of compile time programming to figure out these kind of things. It requires a lot of knowledge about the system and how you kind of configured it to be able to figure out those type of high-level things. The code only really can see what function calls are being made, but doesn't know what these function calls really mean for the most part. It just kind of sees, oh, some instructions here, some instructions here. It can see, oh, this is pretty much going to boil down to this, so it can kind of optimize those instructions. Like doing some mathematics, like, oh, this is all constants. I can just do the math right now and then crunch it down beyond that. Next step higher, it's not really possible. It's not at the moment. But give Google like a couple of years and lots of machine learning, I'll figure it out too. Yes.
So going back to the ground routing, the quantity I was thinking about, so it's nice for responsiveness that kids can do their thing at a time, but turnaround time to the time for jobs getting completed, and so for that you want the short jobs first, and FreeRTOS manage that. So that
If you can know which jobs are shorter than others?
yes, but you do that by dropping the priority no longer you are in ground routing.
Oh, interesting. Okay, so that goes into that goes into a scheduling problem that goes way down. What FreeRTOS kind of guarantees for you for the most part. But I'll tell you right now, FreeRTOS does not do that for you, and they kind of put it on the user to kind of figure those kind of things out. But I will tell you this. It is an active problem that people are still trying to solve and improve the problem. Like, okay, given some statistics about how this particular process was running, can we determine that this one's going to take just be completely CPU bound, it will never sleep, it will never finish, it will just keep doing its thing? Can I get some other smaller tasks done in order to like get as much processing done across as many tasks as possible. Also, the other question actually would be in there is, do you even want that? Could it be that, like, besides prioritizing the smaller tasks, you really want, like, the other ones to keep kind of be in between the folds? If you create, there's hardware, the Intel chips actually have hardware that kind of does some work for you on that side, and there are people writing algorithms to kind of handle that, but that goes beyond FreeRTOS, and most RTOSs will do that. Although VxWorks may actually do that. So. Any other questions? Those are good questions. Yeah, no, I mean that's what a class is for.
The last lab, not yet. But then the last lab, basically calling a lot of really today and all that, right?
Yeah.
No more into that because it's already done. So after it's an easy lab.
Yeah, it is. It's basically take whatever like sections, like, oh, this is doing the keyboard, this is doing like this, and this is doing that. Put them in their own tasks. Let them work it that way. One thing on that one though, and this is what the next lab is going to be for, is going to be going into some of the weird things that can happen when you have tasks randomly switching contexts, and you're writing some data. Oh, I was going to write some data to the global variable. Then halfway through writing the data to the global variable, the other task got swapped in, and it's like, hey, the number used to be like, something reasonable, let's say 10, 15. Now it's, negative 1 billion. Like, what happened here? So that's something we'll go into next week.
So I have the last question is after, let's say in the middle of key part function, right? So the guy key in the number 1,000, so 1000. But then because of the scheduling problem, now you go on to execute another task. And then in the middle of that, the key already dials and redials. And then he's ready to pass another one. Would it be faster than the scheduler, or scheduler guaranteed still in the window? You don't miss any either.
Depends on what your delay time is, but if you're doing like that, kind of goes into like how fast is the rebound time for like when a person quits. I think the millisecond is a decently small duration to be able to catch that for the most part.
That's why they set that to be small.
It's usually because like a lot of from what I've gotten and gathered from a lot of the people is that it ends up giving your task enough time to build well. Because if it's work done, that means that the task can be swapped in and worked on at that particular time as well. So if it gets to the point where delays, other tasks kind of get swapped in. But it's just one of those, I guess, kind of, it's one of the rule of thumb that I really have here, which is that particular time ends up being reasonable for most applications. And I actually think Lamb Research does a lot of the robotic arm stuff at 10 milliseconds specifically, which I found to be odd, but I think they have external controls that do all the motor controls like that, so that is that time specifically. Cool. Awesome. Yes. I'll see what I can do. Yeah, I'll send some links about like where documentation can be found, some like tutorials on the website as well. Yeah, I did that. Oh, that's 152. 152 is a pilot bus. Let's see that. We've got 7 more. No, that's my pilot. No. I don't think it's from what I remember, embed is just a set of, it's basically a set of, no, so they call it all this on bottom frame. It has everything kind of done for you, for example, like setting up IO, setting like main order size, things like that. But I don't actually know if it has after a while, let's check to see real quick if it actually has an RTOS. So they do have their own RTOS.
Yeah. It's different from
correct, yes, it's not an RTOS.
a lot of it can be put on this. But then the big count of the so we have secure limits like the Atlas ecosystem. Yeah, there's one about that. I can talk about it. Yeah. Honestly, I would say current FreeRTOS because it is. And then there's one company that has embed, NXP thing. Then embed, and also TI, and you also have 15 is the final exam. So your slide 16 is set. It's more likely that whenever you're responsible, that they'll either expect that you know FreeRTOS or anything else, and then they'll train you up from that point. But they won't be able to you did embed. No one's going to do embed, so I guess we'll kind of do this. I feel like I'm going to teach from scratch. Or they're not going to do FreeRTOS because I all the way from most of them do FreeRTOS. So it's kind of like when I was applying for land, they said, hey, we use small talk here. And I was like, neat. That language I'm not being used. So if I come here and I learn this, I'll be good at this particular job, but I will not be able to use anywhere else. Sometimes proprietary, it's just unused. They only use it because they used it back in the day when they were like big and it died and they never switched to it. Other topics. So that's pretty much that's why for you as a young undergraduate, someone who's undergraduate, I highly